Thank you. Yes, so I will be starting by trying to explain the question that I want to try to answer with these 3 lectures. And this goes back to Bob Harper's picture, where he had logic, types, and categories or something like that. So there he had, let's say, intuitionistic logic. Then at the level of so what should we do? And conversely here. So I cannot write anywhere. So this works?
Yes, sir.
Okay, good. Oh, this is bad. Okay. So, intuitionistic logic, and then something like simply typed lambda calculus. That was the type theory counterpart for it. So this was just about proving propositions. It was about provable, and these were about language of proofs. And this was all, and then categories of a certain kind. Okay, and with Steve Woody, we will learn probably about Cartesian closed categories and things like that. So all this line was built around systems in natural deduction. So what you have seen in the lectures of Frank, the first 2 lectures, you have been introduced to natural deduction. Okay, so this line was, the black means natural deduction. Now, today, we have seen sequence calculus for the first time. So I should write here, logic in natural deduction. Okay. Now I take the same logic and I don't insist on intuitionistic for some reasons that I will explain. So it will be actually more linear and classical logic I will be interested in the first place. So let me remove this here and speak about linear and classical logic. And the question that we would like to answer here is, what is a good language that matches this particular way of speaking about proofs? And that's the first question, just for the sake of knowledge. And then the second question is it interesting? So what is this useful for? And the claim of the lectures is that it will help us. I need the blue, which is not sticky. Claim this question mark is going to be a good language for the analysis of simply typed lambda calculus or of other languages. So it's also going to be a good intermediate language if you think in terms of implementation. So if you begin to think about the operational semantics of the language, the abstract machine that will implement this language will be actually very much described at this level here. So the claim is that sequence calculus is more or less the Curry-Howard correspondent for sequence calculus is a formal language for abstract machines, for functional language, something like that. Okay, that's the general theme. So now, how am I going to split the 3 lectures? Well, lecture 1 will be very much about linear logic. So we will carry a little bit of this program in linear logic. So since linear logic has not been introduced in these lectures, this will also count as an introduction to linear logic. So lecture 2, we'll try to carry the same program for classical logic. And we will then face the problem of what it means to have a constructive presentation of classical logic. So some of you may know about the extension of Curry-Howard made by Tim Griffin in the early 90s. Or others of you may know about Girard's work on logical system, constructive classical logical system called LC. And that's very much what we are going to see tomorrow. And lecture 3 is meant to introduce you to a very powerful technique which is called realizability. So again, it will be here classical realizability. And I will show you how to prove strong normalization for the system introduced in lecture 2. And out of this proof, you will get through translation the proof of strong normalization for called by name or called by value simply typed lambda calculus. And I even claim that realizability is best understood probably in this framework, because you will see that this language, being lower level in some sense than the simply typed lambda calculus, decomposes things in such a way that all the ideas of realizability in some sense fall into small pieces that fit very well together. But maybe it's a matter of taste. Okay, so that's roughly the plan. And you will hear more about these ideas in next week in Amal Ahmed's lecture, where she will talk a lot about logical relations, which is a binary version of what I'm going to tell you, because I will need only unary predicates to speak about normalization, but you can use the same ideas for programs related with programs. And so realizability is more or less synonymous to logical relations, and there are other synonymous, so also often referred to as a computability technique. There are many words for the same thing. Okay, and someone in the questions in the questions referred already this morning to the powerful technique of proving strong normalization via this method that carries, for example, easily to second order. Okay, I will not treat second order here, but it's once you see the technique, it's not very difficult to figure out how to do the second order. Okay, so before I start on linear logic, I should say that I have lecture 0, which is starting now, which is introducing some syntactical kit. So introducing some syntactical kit that will be used to build the actual syntax, so to construct the red question mark language here. So I want to introduce some of the kit that I need for that. And I'm going to start with 0 and then carry on with 1. Okay, and before I start, most of the work here is the main worker on this area is Guillaume Munch, who is here somewhere, and he will be there during the 2 weeks. So he's a good person to interact with, and you can interact with me until Friday evening, because I'm going to be leaving on Saturday. And another person involved in this collaboration is Marcelo Fiore, with whom we are discussing something like here, trying also to see what are the relevant semantic structures at this red level. So what are the categorical counterparts, what are the categorical IDs that we would need to have a direct account of IDs that come from sequent calculus. And this is far from obvious. And I put double question mark because this work is not yet really in shape. Good. Okay, so I will make a huge collection of slides available, and in my talk I will just pick a few of them. Okay, I took the principle of adding and adding slides, and well, the slides cover many more things than what I want to say, and they could be even confusing in the fact that I'm mentioning many languages. So please free just to use the slides that correspond to the lectures. And if you want to know more, then and you're not afraid of too many languages, or if you know some languages and want to see the relation, then refer to them. Okay. And I will actually spend probably more time on these two asides, which are quite interesting. So the second one, I already mentioned it, is to try to give you a good idea of why this language, which by the way has a generic name, as the title indicates, so we tentatively call this style of syntax, we call it System L, in honor of Gensen, because L is the letter he uses for sequent calculus, as opposed to natural deduction system, for which the letter N is used. And the point number A is I will try to show you that the rules for the different connectives, so we have seen already a few connectives, follow a quite general pattern that you can best understand with the notion of a general connective, which is quite related to the idea of synthetic connectives introduced by some work of Girard called Ludix. So I will try to say something about it at some point. Okay, so this is a table in which I will only touch at 3 entries. So it's just to tell you that I will deal with a matrix with of dimension 3 in some sense. So we already know that I will speak about linear and classical logic. So these are two different things. And then for each of them, we will have to, well, in the case of classical logic, we will have to go to a more refined notion of proof, which I defer to define today because I leave to Frank the privilege to introduce the notion first tomorrow. So we will have systems that are focalized or non-focalized, and focalized for the moment means just a system with fewer proofs or and more constrained computation rules. Okay? And finally, there will be a distinction between systems in direct style and systems in indirect style. And here I'm referring to the terminology used in the so-called continuation passing style translations, where you say that a construct is direct style before you CPS translate it, and when you CPS translate it, then it's in indirect style. So we will see what this kind of distinction means in this setting. Okay. So the three systems that we will have that we will go through. So today we will go through syntax for linear logic. Tomorrow we will go through two syntaxes for classical logic, so LK. Both will be focalized, and for a good reason, because non-focalized systems are computationally non-focalized. Classical systems are computationally trivial in the sense that you cannot endow a system of classical logic without, with a reasonable operational semantics where you will not identify all proofs unless you do something, and this something is focalization. Okay, so now let's start with lecture 0. So we have seen the cut rule this morning. No, before that, I need also to say some difference, because I'm going to be in two frameworks, the linear logic framework and the classical logic framework, where there is an intrinsic symmetry given by the fact that the negation in the logical system is going to be involutive. So we will have, both in linear logic and classical logic, the fact that A and not A are the same or are isomorphic. But actually, they are going to be exactly the same. So I will use this funny notation for negation. It's not so funny. You find it in books on set theory, for example, as a notation for the complement. So we'll have this by definition, for the good reason that the negation being involutive will be actually defined. It's not going to be an explicit connective in the language. It's going to be defined by the laws of duality. So we'll see that in a minute. So that's a key difference with the treatment of intuitionistic logic. Of course, when we will translate the intuitionistic negation, we will not translate it by this simple-minded thing. We'll need to think a little bit more about it. So it's going to be quite different from this, but the framework that we introduced, that we shall introduce, will allow us also to describe this, to decompose it in some sense, using this involutive negation and using another operation that we will see, and that is called the shift connective. Okay, but this is a bit just an announcement. So that's one change with respect to the intuitionistic flow in the lectures of Frank, is that from the beginning I start with the idea that negation is involutive. And secondly, from the beginning I start with the idea that sequence are symmetric objects. So because you have a number of assumptions, you also have a number of conclusions to have it symmetric. Okay? So we are not going to limit ourselves to a thing like this. Okay? And let me here make a comment and probably put a pointer here, because I need to explain it at some point. So I need, let me just give this as a pointer. At a certain point, I will show you a 2 lines proof of the excluded middle, and you will see why this very short proof relies on the fact that several formulas are allowed on the right of sequence. So it is very important that for intuitionistic systems, the fact that you have just one formula on the right is actually a very important property that guarantees you to remain in the intuitionistic world. Well, but I take the opposite view, and I'm happy with a classical and fully symmetric view of things. Okay, so with these points now, I can start really the lecture 0. So this was lecture -1. And let's take the cut rule and let's try to see how we can transcribe the cut rule in terms of a syntax. So how can we make a term assignment system for this rule? So the first note that the rule is a bit different in formulation than in Frank's lecture for two reasons. The first is that I'm allowing delta to be on the right to have an arbitrary number of formulas, but also I also have distinct, as you see, distinct assumptions and conclusions in the two sequences, and I'm assembling them. Okay, so this style, as we will see in a minute when we come to lecture 1, is referred to as a multiplicative style. Okay, while what you saw in Frank's lecture was in additive style. Okay, so with these two differences, you will recognize the cut rule, namely that you find the formula A on the right in one of the assumptions and on the left in the other assumption, and then you can sort of plug these two proofs together to eliminate this formula. But if you want now to transcribe this syntactically, you first have to notice that if I call delta 1 the sequence A delta prime 1, it might well be that A also occurs in delta prime 1. So I need to be very precise in saying which of the possibly many assumptions A in the conclusion of the first hypothesis I really want to cut. The same thing on the right. So for this reason, our language is going to decompose this rule by some devices that take a sequence, gamma delta, so maybe I can write it here. So I have a sequence gamma, let's call it like this, okay? And I want to say that the rule that I'm going to apply to this sequence is going to make this formula active. So the notion of active formula means that it's the formula which is important for this rule. So you see that A is the only named formula here in this rule. So we want to make this formula active, and for this reason we will introduce explicitly different kinds of sequence. So we will have ordinary sequence and a syntax for them, and we will have sequence where one formula is active, and we will have explicit coercions between them. So now let's look precisely what we do here. So when a sequence has no active formula, I'm just imitating what we do in natural deduction, where all the assumptions are named by variables. So here we are going to name not only the assumptions but also the conclusions. So the assumptions are going to be named by variables, x, y, which we will call variables, just like for lambda calculus. And for the conclusions, the assumptions, the formulas, will be named by letters alpha, beta, etc. For those of you who know about the lambda mu calculus, this notation is taken from there. And they will stand for what are called continuation variables. So now, suppose that I have a proof of this sequence, and I want to say that now A is active, then I will apply a binding construct to this proof called C, and I will call this binding construct mu. And this mu is exactly a variation of Parigo's mu in the lambda mu calculus, again for those of you who are familiar with that. And on the left, I'll do the same, except that I use a mu tilde. Okay? So the idea, just as in any binding construct, is that mu alpha dot C has the same free variables at C except for alpha. And this corresponds exactly to the situation that now I'm speaking about a term of type A in this context. So I have excluded alpha from the context. I have abstracted it away from the context. So it's really where should I go? Okay. So in order to account for the cut rule, so I need to activate this occurrence of A, named alpha, this occurrence of A named X, and once this is done, I can say that I plug them together, and I have this syntax for that, which you can read as place this term V in context E. And maybe you can begin to understand why this language is going to be good for abstract machines. Because when, or even for operational semantics, when you do operational semantics, you explain how to evaluate an expression in context. Okay, and this goes back to early works of Matthias Feleisen on formalizing this operational semantics of the lambda calculus. So you can really think of this as being the context in which a given subterm is evaluated. Okay. So let me summarize. So what we have is not exactly sequent calculus. It's a more detailed form of sequent calculus where we, in order to have a precise syntactic account, we have been led to introduce three kinds of judgments instead of just the notion of sequent. So we have ordinary sequence, which in the syntax will be denoted by a syntactic category called commands. And just for the reason I tried to explain here, because the typical term in this syntactic category is really like the state of an abstract machine. So, like a command. And then you will have terms of type A on the right, which look like the familiar lambda terms, or the familiar terms that we have seen in both Bob's and Frank's lecture. And symmetrically, we will have context which you have to think, so you have to read this as E is a context who is expecting in its whole a value of type A. So the type of the context is not the type of the resulting term obtained by filling the context, it's the type of the whole of the context. So that when I do the cut, I really have the same formula, because I fill the whole of the context with a term of the same type. Okay, and in the next lecture, tomorrow, in order to solve the problems arising with linear logic, we will need to have focalized systems. And to account for this, we will also use a fourth kind of judgment, actually a fourth and a fifth. We will consider among terms some special terms which we shall call values, and among contexts we will need special contexts which we shall call co-values. But this we'll see more of it tomorrow. Okay, so now now I want to introduce another idea. So, and other pieces of syntax. So far what we have seen, let me summarize what we have seen of our syntactic kit of System L. We don't have seen much, but still. We have seen C, and C is obtained by plugging a value into context E. And then we have seen an example of V, which is mu alpha dot C. And you may suspect that you also have variables. And for E, we already have seen mu tilde x dot C, and you suspect that symmetrically alpha is going to be a context. So now I want to discuss a form of conjunction and a form of disjunction. So, and I want to preview, but just briefly, a distinction that will be made clear by the lectures of tomorrow, which is a distinction between reversible and irreversible rules for presenting connectives. So I want you to read the rule on the left, remove the term information, think of the tensor as a conjunction, and then I would like someone to tell me what is the difference between the rule, which is here, and the rule that you have seen in Frank's lectures. So can anyone tell me what's the difference? Disjoint context. Yes, disjoint context. The fact that contexts are being piled up rather than shared. Okay, so it's a difference. And now, think of this rule in terms of proof search. Is it the same? Does the conclusion of this rule amount to the same thing as having the two assumptions of this rule? So I'm telling something informal here. I will say that the rule is reversible in case there is the same amount of information in the conclusion of the rule or in putting together the assumptions. So can anyone give me an argument why Frank's rule was reversible or irreversible, and why this rule is, well, irreversible because it's already written? So what makes it irreversible?
So this rule, it seems like this rule is irreversible because you don't know which parts of the context go with which of the two projects.
That's right. So if in terms of proof search, decision, you have to allocate resources, and so you take a risk. While in the formulation of Frank this morning, you just share the same context, so it's easy to see that the rule is reversible. You have the same amount of information. So in other words, as far if we take seriously the rule that we use to introduce the conjunction, Frank's conjunction of this morning is not the same as this conjunction. And by the way, I use a different symbol. Okay. So now, the rule on the right is even more different than, so think of this as a disjunction. So it's even more different to that of this morning. Okay? Frank's rule of this morning was widely and even more obviously irreversible because it was saying that from A you can deduce A or B. Okay, but this clearly is not invertible. From A or B, you don't know A. But this rule is also perfectly understandable under, of course, I forgot to tell you that the intuitive reading of a sequence gamma entails delta. Oh, sorry, I don't use Frank's notation for sequence. I just use the same turnstile. But since I'm mainly talking about sequence calculus, it's a homogeneous notation. So anyway, so the intuitive reading of this is that the conjunction of the formulas here entails the disjunctions of the formulas here. So with this understanding, it is clear that having the formula A1 or A2, or the sequence of formulas A1, A2, on the right of the sequence has exactly the same amount of information. Because the A1, A2 is just another way of speaking of A1 or A2. So this is also a perfectly sensible way to introduce the disjunction on the right. And it's the reversible one. And now I can complete the point I wanted to make here. Once we take this rule as primitive, then we have a very, very cheap proof of the excluded middle. Namely, if you want to prove A or not A, well, apply the rule for introducing the disjunction on the left, apply this rule, and then this is a version of the axiom. You will recognize A entails A. That's the axiom, but if you move this formula to the right, it becomes its negation, and then this is the axiom. Okay? And you see that you have this very cheap proof of the excluded middle by accepting that you can have several formulas on the right of your sequence. So that's just to stress the point that one of the firewalls that the intuitionistic systems put against this principle is by maintaining just one formula on the right of sequence. Yeah.
Can you explain the notation again? Like for mu alpha dot C virtual bar accidental?
Okay, so the vertical bar is the usual. So a V is either this or this. Okay, and the mu alpha dot C is this coercion that allows you to activate a formula. So you start from a syntactic category and you end up in another one. Okay? We will see them in action. Okay. So now let me take these two rules which I have justified, and I have given these names to the connectives. That these names come from linear logic. So this is a notion of disjunction. This is a notion of conjunction, and they happen to be dual to each other in linear logic. And the dual of a reversible connective in linear logic is an irreversible connective. So now, for irreversible connectives, we make the choice that the syntax will use constructors. So from a term, in order to build a term of type A1 and A2 in the irreversible style, I will just assemble a pair of two terms of the respective types A1 and A2. For the reversible connective, I will use pattern matching binding constructs. So it's a slight variation on this same idea of a mu, because what we shall do is instead of taking two terms, well, here we just have one assumption. Instead of taking one term, we wouldn't even know which term of which type to take in this rule. Notice that A1 and A2 are relevant formulas to build A1 or A2 in this formulation of disjunction. So you would come up, if you had to sit down and try to think how to formulate this rule, you would probably come up with the idea that the assumption should be a command, because you wouldn't know exactly which formula to activate, because you need to activate both. And then you form a term of type A1 or A2. So you add a case here to this syntactic category by a mu construct, but which is now a structured mu construct. It's not a mu alpha. It's going to be, okay, sorry, it should be an alpha 1 and an alpha 2 with my convention. So you will construct mu alpha 1, alpha 2 dot C, and that will be our syntax for building terms for reversible connectives. So why is this way of doing syntax sensible? Just because when we are going to cut a term T1, T2 against a term of dual type, A1 or A2, computationally, we will just have to pattern match T1, T2 against the pattern X1, X2, and then substitute T1 for X1, T2 for X2. So the cut elimination rule will be accounted by very simple programming language IDs and principles. Okay, so that's the choice that we try to uniformly adopt. When you will see irreversible connectives, we will use constructors. When you will see reversible connectives, you will see a mu or a mu case. Okay. Yeah, sure.
Are you going to be introducing the mu to the context, or should that be mu taken?
Oh, okay. So here you see that in these rules, I have nothing on the left of the sequence. So in the rest of this lecture, there will be nothing like this syntactic category. Only terms V will be considered. Sorry?
To be a language expression, and then you also have these two extra things that you have on the board?
Yes, exactly.
Okay.
So then
1, T2. These all fall into this category. But, okay.
So the right-hand side of the configuration, you have this third production there of the E.
Yeah, the third production is in the case. Sorry, yes, this because up to here I try to introduce my IDs with two-sided sequence, which is probably the best way to understand the things from the programming point of view. But for the sake of economy, of the number of rules and number of things, I will turn now to sequence that has this form. And when you have an involutive negation, you can do that easily, because you can bring everything that was on the left, you bring it on the right by taking its negation. So that's why in the rest of the talk from now on, you will not see this judgment context. Okay?
in your commands, you have
Okay.
values on the
Yeah,
left.
you're right.
Values on the right.
You're right. So
So
then, sorry, it's something like this, okay? But actually, it's going to be something like this. So I'm not going to do too much of polarities today because I want to defer this to tomorrow. But you see that I always assemble it was clear in this discussion here that this has as type an irreversible or positive formula, and this has as type a reversible or negative formula. So my commands will always plug together a positive term with a negative term. Yeah, thank you for the comment.
So that also explains a little bit. In the previous version of the document, we have the same formula that was cut one in the context and one in the inclusion.
Yes.
And then we cut between two different structures.
Exactly. So yes. So in the bilateral formulation, you have that is very easy to follow, while in the monolateral formulation, it's a bit more difficult to follow. You have to think that you cut a formula A against its negation. So that's the formulation of the cut rule in the mono-sided version.
I don't see the negation of the tensor is a bar.
Yes. Yes. So this is coming. To finish lecture 0, yes, by summarizing very briefly what are the features introduced so far. So we have introduced different kinds of judgments to account for the way in which proofs are built in sequence calculus. And so we needed to have a notion of activation of formula. And I just want to comment here that we can, with the kit that we have introduced so far, we can also do the reverse coercion. So suppose that you are building a proof where you have introduced, for example, the last formula you have introduced is this A here, V of type A. But suppose that your next step is going to introduce a new formula using now one of the formulas in delta. Why not? You can build your proof by changing the formula you are working on. So for this, you will need to activate a formula in delta. But before you are allowed to do this, you need to deactivate the formula A. So what you need to do is to deactivate formula A and then activate the formula you want in delta. So how can you deactivate? Well, you can do this. So again, sorry, I'm in the two-sided world. I'm using a special form of cut where I cut the term of type A with the context obtained by applying the axiom. So V plugged in context alpha has the right type to be just a sequence. It's a command. So this is a little trick to do the deactivation. And then you can build proofs by combining proofs that actually introduce connectives, and you can activate and deactivate formulas according to your needs. Okay, and the second feature was this notion of structured pattern matching. Okay, so now let's move to linear logic. So linear logic stands in this slide. So let me just make a few remarks. First, the axiom rule has no context. So it just contains, so this you can read this as A entails A, just that it is now monosided, so I have taken the dual of A on the right. And the contraction rule that was mentioned this morning and the weakening rule that was not so explicitly mentioned in the previous lectures, I think, are accounted explicitly and separately in linear logic. And they can only, so these are here, this is the weakening rule, and this is the contraction rule. And you see that in linear logic, weakening and contraction are not allowed on any formula. They are only allowed on formulas bearing an explicit modality, which is called the why not. So the syntax of linear logic contains connectives for disjunction. So maybe we can come back to this just after. So here, the first line gives you the syntax for linear logic. So you will have two conjunctions and two disjunctions. I will come back to that. So that the tensor and the par are the two, no, sorry, the tensor and the width are the two conjunctions. So that the width is the ampersand symbol, and the two disjunctions are the plus and the par, and the par is this symbol which is the fourth in the sequence. It's the ampersand that is returned. And we have in linear logic a connective which is called of course, and its dual which is called the why not. And they are there to control the use of weakening and contraction. So then the next observation is to see that if I had an unconstrained contraction and an unconstrained weakening rule, then the two rules that are given here for introducing a conjunction, the one for the tensor on one hand and the one for the width on the other hand, would be intertranslatable. So it's exercise to show that in presence of unlimited weakening, so forget about these funny signs, if you accept A gamma here, if you accept from A gamma to A gamma, then from assuming just one form of conjunction, you can derive the other one using some contraction and some weakening. But of course, as soon as you constrain contraction and weakening to occur only on certain formulas, they are not equivalent anymore. So that's why they were introduced as different connectives in linear logic. Now, we will see tomorrow that there are also good reasons for keeping them distinct, even in the presence of unlimited weakening and contraction, because they have different computational behaviors. And as such, they could also be considered distinct. But from the history point of view, the notation and the ID comes from linear logic. Okay, so I think we know by now all these rules, because we have seen either in the slide here, or in Frank's lecture. So this morning, what we have seen was a plus and a width. So in terms of linear logic, what we have seen this morning are additive connectives. I will present this terminology in the next slide. And So we have seen in Frank's lecture the plus and the with. And we have seen in the slide just before this new form of disjunction called the par and this new form of conjunction called the tensor. And these two connectives are called the multiplicatives in linear logic. And we have seen the cut rule, we have seen the axiom, and now we need to comment on these two rules here, which are, because we have now a new connective, which is this modality called the bang or the why not, I also need to introduce this, this connective if I want to follow the general scheme of sequent calculus. So the idea of this connective is to think in terms of resources. If I tell you bang A, it means that I have an unlimited amount of A. So I think now of A not as a formula but as a resource. Like, for example, a $1 bill. So having a bang A in my pocket means that actually if I want an item that is worth $1,000, with my bang A, I have no problem, I can buy it. Okay. And if you think of the why not A, it's a more dangerous thing. So A is again $1. Now, why not A is some dollars, but I don't know exactly how many. It could be 0, 1, 2, 3, or 1,000, or I don't know, many millions, billions, but I don't know. So now, if you have this in mind, this is quite easy to read. The first rule, just put this on the right, the question mark gamma. So on the right, because the dual of question mark is bang, it means that if I have an unlimited amount of the dual of gamma, I have A. But since my amount of assumptions is illimited, I can repeat it. So I can get also an unlimited amount of my conclusion. That's the reading of this one. And the reading of this one is that just what I told you, the dangerous thing. So I can take a risk. I have $1 in my pocket, and I decide to turn it into N $. So it's like going to a casino. I can, well, no, in the casino it's worse because you can really lose money. Here you just cancel your money. You cannot go negative, but you can get 0 or an enormous amount. Okay, and so in terms of reversible and irreversible rules, this sounds very much reversible or irreversible, this one? Reversible, and this one irreversible. So again, you see that the dual connectives have this duality between reversible and irreversible. Okay, so now let's summarize. So I've been using a lot this notation of De Morgan dual, or the negation as a defined connective. So let me be now precise. So the involutive negation is present in the syntax on atoms only, because for the rest it is defined. So the dual of the tensor is the par of the duals. The dual of the plus is the width of, I don't know, there is a funny symbol there, probably a misprint. So the dual of the plus is the width of the duals. The dual of the bang is the why not of the dual. And conversely, I mean, the dual of a par is the tensor of the duals, etc. Okay, so now let me give a word of terminology, only a word, about the terminology used by Girard in his founding paper in linear logic. So he divided the connectives of linear logic in 3 groups and called them respectively multiplicatives, additives, and exponentials. And I can give you a very quick explanation and a very good exercise to practice on the rules of linear logic. So the explanation for this terminology comes from the models of linear logic. So I'm touching here on the right side of Bob's picture, trying to give a very, very quick introduction to the idea of a very simple and even a bit too degenerate model of linear logic called the relational model of linear logic. So it's like denotational semantics. I want to give a meaning to formulas, and I want also to give a meaning to proofs. And that's what I'm going to do. So formulas are going to be interpreted as sets. But you have not to think about the elements of these sets as being the meaning of the proofs. The elements of this set are rather to be thought as tokens, information tokens, that you put together in order to obtain a real data. Okay? So that's why formulas are interpreted as sets and proofs are interpreted as subsets of the corresponding type. So the model is degenerate in the sense that it interprets dual formulas in the same way. So it cannot see the duality. So the tensor and the power are both interpreted as the Cartesian product of the two interpretations. The plus and the width are interpreted as the disjoint union of the two sets. And the bang A and the y naught A are interpreted by the set of all finite multisets of elements of A. Okay? So this should explain very clearly, except for the last line, the terminology used. Because everyone knows the cardinal of a Cartesian product is the product of the cardinals. So it's a multiplication, while the cardinal of a disjoint union is the addition of the cardinals, so it's an additive thing. Now, for the third line, for the fourth line, and well, yeah, I forgot to tell that for atoms you have to make decisions. It's like everywhere in logic, when you begin to interpret a syntax that has variables, you have to make choices. Okay. So the fourth line, if you follow me, isn't quite exponential in the sense that if A has finite cardinal n, m fin of A is going just to be an infinite set. Because if you take the finite multi-sets of elements of a set, then you can take A as many times as you want, so you have an infinite set. So it's not quite exponential. But it happens that there is a variation of this. So the first model of linear logic was not as degenerate as this. It had a way to distinguish duals, but for this you need to introduce some relation between your tokens. You must say when your tokens are compatible or not compatible, and then if you have this notion, you have enough information to make different interpretations of your connectives. And then with this, so this is called coherent spaces. And with this interpretation, then you have another way to interpret the bang, which is a little bit less invasive in terms of explosion of numbers of tokens. You just take here the finite subsets of A. And then you see the reason for exponential, because this is precisely the relation in cardinality between a set and the power set of this set. But for reasons that are known to the logic community, the linear logic community, taking the finite subsets just in the relational setting doesn't work. So you need to have the coherent spaces to make it work. Okay, so the exercise is that you take all, there are not so many of them, take all the proof rules and try to execute this program. Give explicitly the interpretation of the proof of the conclusion, knowing the interpretation of the proof of the assumptions. And then you will understand why the multiplicities are really interpreted as Cartesian product and the additives as disjoint unions. Okay, so I have about a quarter of an hour. Yeah. Okay, so now in the last quarter of an hour, I will complete the description of this syntax, which I already sketched, to cover all the cases of linear logic. So what I'm going to do is to turn this proof system, which has no decoration by terms, and to give you term decorations for all of them. And this is given here. So in this monolateral presentation, I don't use x and alpha for variables. I just use x, even if it's on the right. So the axiom tells me that if among my assumptions I have tells me that well, it's the axiom, but it tells me that x is well typed of type A in context x of type dual of A. Now, the second rule was not present in this because here we only had one kind of sequence, but we have seen that in order to give a syntactic account, we want to have different kinds of sequence. So that's why we have now the mu construct that allows me to coerce commands into a sequence where one formula is active. Now here you recognize the cut rule that has already been discussed. You recognize the formation of the tensor that we already discussed. Now you recognize Frank's introduction for the disjunction, and quite naturally I will use, so since Frank's disjunction was irreversible, I use constructors, and I use quite naturally the in-left construct, thinking of A1 plus A2 as the disjoint union of A1 and A2. Okay, same thing for in-right. Then we have already seen the par, and so this is the rule for the width. So this is a bit more complex because you could think, well, it's a width, so I could make the pair of two things. Okay, but I prefer to reserve the notion of pair for the tensor that was line above. So here I follow the scheme. Because the width is a reversible connective, I apply the general method in the general philosophy in this syntax to say, well, I need a pattern matching construct of that. So, or a case construct. So that's the syntactic account of it. So I have a command of for proving A1 gamma. I have another command for proving A2 gamma, and I assemble them in this way to form a command of type A1 with A2. And in order to convince you that this is sensible, let me give you immediately the computation rule corresponding to it. So you see that I need to match somebody of type with somebody of its dual type, which is plus. So I'm going to plug it either with an in left of T1 or an in right of T2. So this is accounted by the fourth line in this slide. If I plug in left of T1 with this mu construct, I choose the left branch of the mu construct, throw the C2 away, and substitute T1 for X1 in C1. So again, you see this pattern matching in action. Okay? So for the last rules, I will not insist too much because we will not deal too long with linear logic, but I do it a bit more briefly. I told you that the introduction for Bang was irreversible. So again, sorry, it was reversible. So again, we use a binding construct for that. And for introducing the why not, I said it was irreversible, so we use a constructor. And again, if we match a guy of this type with a guy of this type, what we will do is, again, the same style of reduction. So this is the line in red. We just remove the Bang decoration, substitute T for X. So you see a uniform scheme in all these rules. And we will see tomorrow at some point in the lecture the notion of general connective, where this idea will pop up very clearly. So there is a generalization that has as instances all of these lines. And finally, for the time being, just for the sake of the last 5 minutes or so, I will use explicit notation for the weakening rule and the contraction rule. So I just mark explicitly that I have applied a weakening, and I just mark explicitly that I have applied a contraction. Okay, so now in the 5 last minutes, I want to discuss something that has not been discussed so far, which is, we have seen some notion of reduction in the lectures of Frank, but we have not yet seen a discussion of confluence. That means, do all the computation paths lead to the same result? So an important feature that we are seeking, both for linear logic, for intuitionistic logic, and for the version of classical logic that we will see tomorrow, in all these situations, we seek for confluence. So let's see why we can be confident that the reduction system that I just gave here is morally confluent. And I will tell you what morally means. So, as you probably know, I guess that everybody of you has had some kind of introduction to the basics of rewriting systems. You already probably all know that in order to check that the system is confluent, you have to look for so-called critical pairs. So that are terms to which you can apply two rules and follow two different computation paths, which you have to complete to get a unique common reduct for these terms. So the critical pair in these systems are listed here, but I will only analyze the first one. So you see that, oh, I didn't comment on the first two rules, sorry. I commented on all the rules except the first two. So I introduced this mu and this, yes, the mu construct. So the mu construct has this behavior. It's just, if you are used to beta reduction, it's very similar to beta reduction, except that the mu doesn't have to do anything with implication. The mu can be of any type. Okay, so it's the only difference, but otherwise it's really like a beta reduction. So you see that if you have a term of this form, mu x against another mu x1 against another mu x2, you can choose to apply the red rule, the rule that will substitute the right-hand side for x1 minus, or the contrary. So you can read the slide in more detail, because I'm not going to comment it in too much degree of detail. But by analyzing, because the syntax so far, as I have introduced it here in this slide, because the syntax is linear, what does it mean that the syntax is linear? It means that in every term, when I see a variable, in a term, a variable occurs exactly, in a free position, occurs exactly once. That's what a linear syntax is. And the fact that the syntax is kept linear has to do with the fact that I have these explicit notations for the contraction and the weakening. So because of the linearity, it's not difficult to see that this x1 minus occurs, as I just said, occurs exactly once in C1. So C1 must have the form, it's a big term, and a hole in this term has the form x1 minus cut with something. Okay? If you remember, this was the syntax for deactivation. So the same thing for C2. So now, if I apply first the mu x1 minus rule, then I substitute for x1 minus the term on the right, okay, and after a second step, what I end up with is with this term called C1, C2, T1 plus T2 minus. So the important information is that I'm piling up the context capital C1 and capital C2 in this order. While if I had chosen symmetrically to reduce the mu x2 plus first, then I would have piled the context in the reverse order. Okay? But now we have a very simple geometric picture to contemplate. Namely, either do this and then that, or either do that and then this. Okay, it should be blue. It should be blue. And it's not difficult to figure out that you can praise this if you have enough rules of commutations. So the idea is that you have introduced connectives in some order here and in some other order here. But you can change this order if you give yourself, and it needs a little bit of patience, and this should be written in some detail somewhere. Has not been done fully, as far as I know. But I just want to give you the idea. So if you accept these elementary commutations as being modulo rules, that means that you reason modulo these commutations, then you get confluence. So that's why I said the system is morally confluent. So now my last observation is what would happen if I had not a linear syntax. In particular, what would happen if I had unlimited contraction and weakening, then this argument would not work anymore. And we will see tomorrow that instead we face a wild non-confluence problem. So on one hand, we have a confluent system given by linear logic using the following restriction, which is a restriction by types in some sense, which tells me that contraction and weakening can be applied only to certain formulas. That's one way to solve the difficulty that we will see tomorrow with classical logic. The other way will be not to restrict the classical logic, not to give any kind of restriction on the rules of classical logic, but instead to give restrictions on the computation rules of classical logic. And that's the route followed by focalization. And that will be the subject of tomorrow's lecture. Okay, thank you. Questions? It's just when you write any of the rules that you have seen in the lectures the day before yesterday, you always have seen things like gamma proves gamma, which is always a context, and then there is one formula. Okay? That's the formula which is introduced by the rule. Okay? So typically, I don't know. Let's go back to any of these rules. So let's pick the one for tensor. I don't care what is in gamma, I don't care what is in delta, I just put them together. While A1 and A2 are active formulas because I'm building something out of them. So it's better to think of the other formulas as not being active.
So these are put in as administrative reductions in your calculus to just go through your context to see what you want to do, or what?
Do you mean the formula in gamma delta? Well, yeah, they are the three variables.
Are you asking about the two different judgments? The one with the bar after it,
right,
just has this the output bar?
Right. So it seems like, since this has no account of active mostly, pulling things out of context, that the notion of active and context is administered so that the abstract machine can go through and flip around inside the context. Is that not the right way of looking at it? I'm really quite confused.
Well, I don't know. We can look at one and some of the rules again.
Can you go back one slide? Is it the top right rule that you're talking about? The administrative, like the extra rule?
So another way to look at all the right-hand sides of the rules, of the computation rules. They all have the shape, a term t replaces the variable x. So the term t is either a negative or a positive term, but it's always an active, something that has been obtained as the result of the rule, and always something active. and it replaces a variable in the context. If you want to replace a variable, you need something of a given type. So you need to have activated this type. That's the idea. Doesn't make sense to me. A command has no type, except that it's in the drafts in the context. Gamma and delta, but it has no type.
So why not use these substitutions in the rules themselves? Why not use these substitutions in the rules themselves?
Okay, that's a good point. So this system here can be read in two manners. It can be read in the style of explicit substitution, where this substitution should be actually carried out, and this would require some work. Or it can be read in the style of the lambda calculus, classical lambda calculus, just do it in one shot. So if you do as in the lambda calculus, then you have a more comfortable life. Because then you can prove theorems just as you prove them for the lambda calculus, and you will do that in the lecture 3. But if we want to account completely for the cut elimination as Frank began to do this morning, then we would need to have an explicit version, and we would see that, well, in the cut elimination process, you have two kinds of cut elimination steps: the nice ones and the administrative ones. Someone who not aware of it. So the nice ones correspond to all the rules I have given here, and this corresponds to two formulas that have been activated just right before the class, or introduced just right before the class. If it's not the case, then I have to commute rules. So in the terminology of Kenton, these are called the commutative cut elimination rules. And this would be accounted in this setting by actually pushing the substitution through the structure of the command. So maybe we should start in. Thank you.